sort of I'm going to try to connect the dots between the viewpoints. Earlier we have introduced the Wickham theorem and looked at the ergodic problem from Wickham theory viewpoint. We have proved the existence of solutions to the Wickham theorem like by two different ways. And actually later on we also used the peer barriers to prove existence. That was the third proof of the existence of solutions to the ergodic problem. So today is going to be the fourth way. So the goal of today is going to be existence viscosity solution to the ergodic problem. Okay, and again, this is the fourth proof in our course, and you see that the PD proof is actually quite different. It's quite simple actually, and I can say that you know so let's say so note that this is the fourth proof in our class, and this proof works for general non-convex Hamiltonian as well. Okay, and the proof I'm giving today is going to be the proof today is from Lyon's Papanicolaou and Varadan work. So Lyon's Papanicolaou Varadan. The proof is not hard. We can actually enjoy it and relax for the Friday. What I want also to show you is that that's the first point. The second point I want to show you is that like what's the kind of a difference of viewpoint between PDE and dynamic system. Okay, by the end, where we consider the whole effective Hamiltonian. Okay, again, as usual, stop me or talk to me if you have question or concern. Okay, so let me recall quickly the ergodic problem here. That is, we find a function v so that h of x dvx equal to a constant c naught in the torus, right? We have proved earlier that c naught is unique and such. In order to make the discussion clear, I want to make right away a remark that surely the equation here E doesn't contain the zero order term. V itself, right? I mean, it does contains V in in the gradient of V, but it doesn't contain the zero order term V itself. And as a matter of fact, that implies that E is not monotone in V. I'll explain what it means. Not monotone in V. I'll explain, and this use out immediately, that that E does not have unique solution, doesn't have unique solutions. Of course, we have already studied about the matter set, which is the uniqueness set of A, right? But I'm now, for now, just looking in a very naive way, in the PDE way. The equation doesn't contain the zero order term, and it's not monotone in V. So this is always the general principle in PD, that if it's not containing the zero order term, then you always have the dictionary that if V is a solution to E, then immediately V plus C is also a solution. Okay, so that's sort of the key point, right? Because if V is always the solution, then you know, like V plus C is always the solutions, and we have at least a family of solutions, and it makes the problem complicated. And in terms of PD language, so in general, for general equations, a general Hamilton-Jacobi equation of the form like I have f of x u du equals to 0, say in the torus, whatever. Here f is the given function, say f x z p is a given function. Then we say that f, the equation, or f is say that the PDE is monotone in U if I have f taking the partial derivative in z is going to be greater than equals to some constant c positive for all xzp. Okay, so in other words, you know, it has to be in the slot the u here, you know, it has to be containing a you know, like lambda u for lambda positive, for example. So it has to be monotone in U. So typically for this kind of PDE, then monotonicity, monotonicity in U, then implies typically the uniqueness result, uniqueness of viscosity solution. Okay. So that's sort of the remark I want to make. And again, you know, as I said, you can see chapter 1 in my book is quite clear about everything, but it's a general dictionary telling us that if the equation is monotone in U, then you have uniqueness of viscosity solution. Okay. So let's get back to again, we're gonna study the ergodic problems E. We try to prove the existence of solution to the ergodic problem. Okay. Um, so let's put the assumption on H. As I said here, we don't need H to be convex. Nevertheless, if we have convexity, I'll tell you we have formula. We only need H to be continuous, and then it's coercive in P. Okay. And as I said, I mean, because we don't have much time to go through the route of proving all the well-postness and study everything about viscosity solution, we are doing it in a minimalistic way. We are sort of cherry picking what's most important, and then, you know, like go with that. And, you know, so the approach of Lyons, Papanicolaou, and Varadan, it's, you know, by now it's a very natural approach. It was a very important result in 1987, still unpublished paper. And you know, the idea is very natural, right? You know that your equation is not monotone. It might have many solutions. So the idea is always, as in analysis, PDE, or in general, right? We most of the time needs to do certain approximations or regularizations or something like that to our original object to make it better, right? And in this case, we are doing nothing out of something surprising. We are adding lambda u for lambda positive, And we consider the equation S lambda to be of this form, right? So I mean, the second part is natural, but I'm adding lambda u to the equation. So I'm doing an approximation process, of course. And for each of the lambda, I have my equation is monotone. So it has a unique viscosity solution. Okay, so that's sort of the gap. So the gap is sort of like, approximate E by adding lambda u to make the PDE monotone. So it has a unique solution u lambda. So you would have lambda u lambda plus h of x du lambda equals to 0 in a torus. And then, because then we would try to pass the limit, right? Less lambda goes to 0 plus to try to pass to the limit to get existent to E, right? Again, that's nothing out of extraordinary, but it's very natural, and um, you need to have a good framework to put things through. Okay. So as usual, again, we're gonna try to pass the limit considering certain asymptotic behavior of u lambda to be made precise. And in order to pass the limit, we would need to obtain a priori estimates, right? We would need to obtain estimates in such a way that we can use certain compactness results. Okay, so the theorem says exactly that. It says that we have there is a constant c independent of lambda, such that you can bound lambda u lambda and du lambda. Okay. So the first thing we do first is that we're going to control lambda u lambda. So the first point is to bound lambda u lambda. This is by essentially considering sub and super solution to the problem S lambda, right? I mean, this is the problem S lambda here. You're considering sub and super solutions, and a natural choice could be, again, I'm just going to write it here. So you would just choose phi to be constant to see what's going on, right? I mean, constant is the easiest way to deal with, the easiest thing to deal with as barriers or as sub-super solutions. So if you consider constant, then you plug into the equation, you have lambda phi plus h of x d phi equals to lambda times c, right? Plus h of x0. You know that this is bounded, right? This is always bounded by L infinity norm of h in x. 0 is just 0, right? So therefore, if you choose c to be plus or minus of this L infinity norm, I think I denote it by C naught, right? Then you're done, right? So C has just to be plus minus C naught over lambda. And that's exactly what I wrote here. So C naught equals to this, then you have phi1 equals to minus of C naught over lambda is the sub-solution. And you have phi2 is a super solution, right? And again, you have uniqueness of solutions, and you have a sub-solution comparison principle. A sub-solution is less than equals to a solution less than equal to a super solutions. So we ended up with exactly this bound. So that allows us to say that, so we have, then we have this implies that lambda u lambda is less than C naught, right? L infinity, whatever. And then you plug it back into the equations. You have h of x du lambda equals to minus lambda u lambda, right? And this is less than equal to C naught. So you have h of x du lambda is bounded by C naught. And this is where we put a very important assumptions about coercivity. So it forces, so coercivity, this coercivity is weaker than superlinearity, but essentially it forces your Hamiltonian to grow to infinity as p goes to infinity, right? So without coercivity, actually there are a lot of problems in practice, like the G equations in flame propagations and others that wouldn't follow the coercivity assumptions. Then we have trouble with bounding the gradient. So what I mean is that these assumptions that we put about coercivity is sometimes not natural. Okay, it's a good assumption, but sometimes in very important applications it doesn't hold. Then we would need to go in a different route to obtain a convergent result or getting certain other bounds. In any case, because of coercivity, you would forces that your gradient du lambda has to be bounded, right? Because if it were not bounded, then h of x du lambda would grow to infinity, right? So it has to be bounded, and the constant only depending on C naught, right? C depending, well, only on C naught and the Hamiltonian and the rate of the growing of the Hamiltonian. Okay, so that's that. So we have a priori estimates. And now with a priori estimates comes to using compactness result to pass the limit. Okay, so so let me record here. We have lambda u lambda L infinity plus du lambda L infinity is less than equal to C. And by the way, I'm also using strongly the compactness of the torus here. When the problem is not in compact set, then this kind of result also doesn't hold. And that's why, for example, stochastic homogenizations, random homogenization is very hard. It's harder. I mean, not crazily harder, but it's harder because the lacks of compactness. So with this, we're gonna use Azelascoli, right? Compactness. To pass to the limit. Okay. Any question or concerns up to this point? Okay, good. So one of the point here that I want to say is that remember that u lambda is not bounded itself, right? U lambda might go to infinity. Only lambda u lambda is bounded. Okay, so we got to be quite careful when we pass the limit. Just a tiny remark for ourselves is that so it's just a tiny remark is that u lambda itself might not be bounded. Yeah, we only have lambda u lambda is bounded. Nevertheless, we are in a compact setting. Although u lambda is not bounded, I have the gradient of u lambda is bounded, right? So I have du lambda is bounded, and we are in the torus, which is compact. This is being identified as 0, 1 to the power n. Again, being identified as is compact, right? So although the u lambda is not bounded, I can normalize it. How do I normalize it? I just subtract a value at any fixed point again, or whatever, or minimum value, whatever you want. We can just normalize it by taking u lambda minus u lambda 0. Okay. Once we take that, then automatically v lambda is bounded. Okay, because first of all, the gradient of v lambda is the same as gradient of u lambda, right? Because I'm just subtracting a constant. Gradient is the same, it's bounded. The v lambda itself is bounded because v lambda is the difference, right? So v lambda x is u lambda x minus u lambda 0. So this one is surely less than or equals to x times with the L infinity norm of u lambda, right? And again, x in the torus, you know, let's be generous, is at most the diameter, right, of the torus, which is root of n. So this is less than or equal to root of n times c. Okay, that's why in the torus is good. So we have v lambda is bounded, right? So so what have we done? Let me write down the scenario here. Well, I mean, let me state then, I mean, by Ascoli first, I have, you know, v lambda is bounded and it's equicontinuous, right? You know, because it's actually equiliptious, right? So you can find a subsequence lambda j goes to infinity so that you have v lambda j converges to v uniformly. And moreover, I mean, by passing to another subsequence if needed, you have, remember that your lambda j, u lambda j is bounded, right? So therefore, you can also see that by passing to another subsequence if needed, you have lambda j, u lambda j converge to a constant denoted by minus c, okay, which is in R, right? So what do we have? We have the following. So let me rewrite the scheme, so the septic. I have this kind of equation, right? I know that u lambda might not be bounded, but I can normalize it. So I subtract u lambda of 0, right? Plus h of x d u lambda x equals to minus lambda u lambda of 0. Okay, right? I am normalizing it so that it becoming bounded, and this is just v lambda, right? So this becomes lambda v lambda x plus h of x dv lambda x equals to minus lambda u lambda of 0. Okay, and now you let lambda equals to lambda j and lambda j converging to 0, right? You see that lambda j, v lambda j converging to 0, it goes away. And by stability result of viscosity solutions, right, you have v lambda j converging to v uniformly. So v solves just the equation h of x dv equals you know, I have minus lambda j u lambda j 0, right? And that's converging to c. So that's sort of already the result we are done. Okay, yeah. So we have proved that there exists a constant v, and sorry, a constant c and a function v, so that it solves the ergodic problem in the torus. You see that the PD proof is totally different from the dynamical system proof, right? Dynamical system, we have to use the Lux or Lechnik semigroup. We have to use in a way, we also use compactness. We use the equi-Lipschitz, uniform Lipschitz property of the semigroup if we go up to certain time greater than sigma. And then we use a fixed point theorem. So you see that in any of the proof, we would need certain uniform estimates, a priori estimates to use compactness, right? There we were using compactness for in the fixed point theorem, or I mean, for the Pierce barrier, it's different because we already have the setting. Here we use compactness to call as Ascoli to pass the limit. So you know, in a way, the philosophy are quite similar, but the PD proof is quite direct, and it's quite different. Okay, questions, concerns, anything that you would like to discuss with me up to this point? Okay. So I'm going to prove that C is unique, but let me go down here to give you a few more remarks. So um, so few remarks. The first remark I want to give is that in the convex setting, then in fact u lambda has some representation formula. The most sort of like well-known formula is the so-called optimal control for optimal control representation formula. Is the following formula, and this is why actually the problem is it's very famous in ergodic control and also in practice. You have this formula: u lambda of x equals to is it lambda? Yeah, I think it's u lambda. So it's equal to the so-called the infinite horizon optimal control problem. So you take infimum among all parts gamma 0 starting from x of the action functional integral from 0 to infinity e to the minus lambda s L of gamma s minus gamma dot of s ds. Okay. So this is why the problem getting it's very famous because it has a lot of practical uses in general. You have this is the so-called the discount term. This is the discount factor, and this is also the problem in like infinite horizon problem. So infinite horizon because of the fact that you start from a point x. This is a point of interest, right? And then you would explore the domain forever. Okay. So you would go about and explore the domain forever. And this part is going, you know, to infinity, right? And to compute this kind of problem numerically or something is actually quite challenging because you would explore the whole space, and then it's a problem of infinite horizon, right? But the discount factor comes into the game so that you have your integral is well under control, right? Because if you don't have the discount factor, your integral can be infinity. That's the first thing. The second thing is that in real life, in a lot of like economics problem, right? When you're selling new products and stuff like that, you start with the sort of like the starting high price, you know, like a lot of new fancy Apple products that they just announced, you know, like with the tax and, you know, whatever. But then, you know, the price being discounted after the introductions, right? So essentially, in certain economics model, they would use this kind of discount factor to determine like what gonna be the price at up to a certain point, you know. So, uh, you know, again, it's a human being behavior, right? So in order to model it, maybe they say that, yeah, maybe discounting in terms of exponential, it's a good thing, you know. So certain things follow this kind of discount problem. For other but it's quite interesting, you know. And you can also see that if you use this formula, um, you can see that right away that if in particular, uh, if you take gamma s just to be over x, then you can see that you can also find a bound for u lambda, right? You would see that u lambda x is less than equals to integral from 0 to infinity e to the minus lambda s. The L is always constant, x0 ds. And if I'm not mistaken, this is Lx0 times 1 over lambda, right? And this exactly gives you the bounds of lambda u lambda. So it fits perfectly well with the PD theory. Okay. Um, yeah, and there some of you actually did ask about. So this is among the space of curves, and sometimes when to pass the limit is actually a very hard problem. So some of you did ask about relaxation. So a relaxation formula along the line of mm, reducing it instead of considering parts. So you would considering just measures. So relax from parts to measures. And it's a very convenient way. Then this is you can see it in my book, and this is based upon the work of Ishii, Mitake. So okay, so it's written in the book, chapter 4 or 5. It's quite interesting because we have certain way to instead of considering the parts, we relax it to measures. Okay, so that's the first remark I want to make. The second one, it's quite well known by now. Let's see my time. Okay, I'm good in time, right? The second one I want to say quickly is that in the compactness result, we have u lambda j x minus u lambda j 0 converged uniformly to v, and lambda j u lambda j 0 converged to minus c, right? The conversion here is only among subsequences. We know that in the limit, the ergodic problem might have many solutions. So the real question was, I mean, it's an interesting question, is that do we have conversions along full sequence? Like, do I have u lambda x minus u lambda 0 converge uniformly to v? It turns out that this question, although that it looks that simple, but it was very challenging. The answer is yes. It's affirmative in the convex case. In the convex case, that was done, but just recently. Recently meaning maybe 5 or 6 years ago. So in the first order case, it was done by Davini, Fatih, Ituriaga, and Zavidovic. So, you know, basically the group. In the second order case, it was done by Mitaka, and myself, and then in the fully, this one is also done in the fully nonlinear, for fully nonlinear equations of this very general form. It's done by exactly the new representation formula I told you by Ishii. Okay, and also that then the problem have been generalized and done for various different settings. For example, you can do it for like problems in nested domains or something like that. If you consider the equations like lambda u lambda plus f for first order, I mean, I don't think it has been done for second order, but in omega lambda and omega lambda converge to omega and something like that, and you, of course, there has to be certain properties. So this was done by Sun here. Yeah, but I don't think that it has been done for second order equations. So I'm just telling you that there are a lot of interesting and important research directions that are going on. Some of them are easy, some of them are very hard, some of them are doable, some of them I have no idea. So anyhow, I'll tell you right away by the end of the class here that there's something that I am extremely interested in, but I can only do some modest results. Okay, so in fact, let's get back. In fact, already in the Wickham theorem, we have shown that, so in the Wickham theorem and earlier, we have shown that C was already proved to be unique, already. But you know, I just want to give you a PD proof, very quick PD proof of uniqueness, and you see that the PD proof is also very different from the dynamical system or earlier proofs. But we're now gonna give another proof, another PD proof for the uniqueness of C naught. Okay. So how do we do this? Well, I mean, let's do it quick. So assuming otherwise, so if you have two pairs, V1, V1 C1 and V2 C2, with C1 less than C2, okay? Of course, I mean, they solve the problem, right? I mean, they solve the equation, but C1 is strictly less than C2. The idea is then that you're gonna, again, the trick of Lyon's, Papanicolaou, and Baradan is always the sort of like the very natural and then same tricks. And actually this one also, this kind of trick, not just working for Hamilton-Jacobi. There was earlier very influential paper by Papanicolaou and Baradan that this kind of idea also works for second order elliptic equations, right? You would just introduce the monotone terms. So, you know, you have a little bit of gap between C1 and C2. So you introduce delta small so that you can squeeze in, right? You know, you can squeeze in delta 1 V1, delta V1, delta V2. Because of the gap, you can just squeeze it in. That's not a big deal, right? You know, V1, V2 are constant, are not continuous in the torus, so they're bounded. You just squeeze in a little bit of the gap, in the gap, it's fine, okay? And the goal is that, you know, when you introduce delta greater than 0 introduced in the equation, then it makes the PDE monotone. Okay, so it makes the PD monotone, and when it makes the PD monotone, then, you know, like then you can use comparison principle, right? Because you have uniqueness of solutions, so therefore you can conclude that V1 is less than V2. right? But remember that we earlier discussed already that for ergodic problem, if V1 is a solution, then so is V1 plus constant, right? So the proof actually give us that V1 plus any constant is less than equals to V2 for any C. Extremely big, right? And this gives us a contradiction, right? That's a very interesting PD proof. You see PD proof using essentially 2 points. The first point is that making the equation monotone so that you can have comparison principle. And then the second point is always that, you know, when we do PD, in anything that I have done, or in many things that I have seen, there's typically needs to be a steps or two or more of approximations, right? You know, and then when you pass the limit, you got to have estimates, right? Some uniform estimates to pass the limit. And that's sort of the way it goes. Okay, so we are done. All right. So now let me tell you a difference between PD and dynamical system. Here it's very tiny, but actually it's a big deal. So in the whole FATI's book and in general for the Wickham community, from the dynamical system viewpoint, we typically only deal with C naught. So, you know, like we just deal with one of the constant and then we master out and then try to understand it. It's already very hard. Now, from PD viewpoint, is actually and actually back to the framework uh, of the canonical transformations. So this is actually this problem. This one is, if we really get back to the framework either of either um, canonical transformation. I mean, the earlier the most classical framework that we try to do change of variables so that we can get an integrable system, or the other framework is about homogenization. Of course, I didn't talk anything about homogenization here, but either of the two framework, what we would need to do is actually not just considering C naught, but I would need to vary the big P. So what I meant is that I would need to think of each of the big P here, and I would need to put the big P in and consider the same problem. Okay. Of course, for each of the big P, the problem, the assumption, everything remains, right? So therefore, for each of the big P, so the problem reads, you know, normally it should be x of x dv equals to something, right? But I squeeze in a big P here plus that. So naturally it should be equals to C depending on big P, right? Okay. Maybe in red. And as I said, for Wickham, people typically only fix big P to be 0 and consider one such problem. From PD viewpoint, and also, you know, homogenizations and numerics, actually it's much more challenging and important to consider the problem for OP. And for numerics, this is typically very hard because computing each of the problem for one piece is extremely expensive. And if you do it for OP, for a lot of P's, it's crazily expensive. So yes, so we have this problem, right? It has a unique constant CP, this unique, and surely it's depending on P, right? So so in the PD framework, we give a definition. So we denote by H bar of P equals to this P, CP. Okay, so set H bar P equals to CP for HP in Rn, and we say that H bar of P is the effective Hamiltonian corresponding to H. Okay, and you see that this is already hidden here. It's a problem about canonical transformation. Why? because you look at the problem, right? H of x, p plus dv of x equals to h bar p, right? On this side, you have h depending on x and p, right? And on this side, you have h bar depending only on p. So in a way, this is essentially telling you that after this canonical transformations, you get to this h bar p here, which is integrable, right? It's only depending on the momentum. If you write out the Lagrange Hamiltonian system, it's going to be straight lines, characteristic going to be straight line, and hence integrable in mathematical sense. Okay, and the PD viewpoint says that actually it's more relevant and interesting to look at H bar and study the property of H bar P for OP, right? So the actually the big deal, the big really big question is to study H bar for OP, or to come up with really efficient numerical computation of H bar. Up to this point, I have been working on this, and I have written papers with some top experts in the fields in numerics, like Jianlang Chen at Michigan State. Computing H bar is extremely expensive. There's not yet any good way to do it. I mean, there's surely ways, but I mean, the question is what's the efficient ways and really great ways, and it's still open. And in the book, I have a whole chapter on, I don't remember if it's a whole chapter, maybe it's a whole section, a few sections on all properties of H bar that that is known up to date in the literature. And I can say it's not much, right? I mean, what we can prove here, for example, if HP is convex, and then the map H bar P is convex, the question about understanding finer properties of H bar, where it's differentiable, where it's twice differentiable, what are the singularity points, and so on and so forth, is extremely hard. And I have been thinking about this a lot, and sometimes we got something, but it's still a very important and mysterious problem to be done. I mean, it's something that we need to go beyond the Walpole's theory. This is essentially like, let me conclude by making a very vague sort of like analogy. Like in spectral theory, right? I mean, once people are done with studying the Walpole's and the eigenvalues, eigenfunctions of Laplace or of second order elliptic operators, they try to study more about the the eigenfunctions, and then also about the nodal sets and all those important properties, and also about the behaviors of eigenvalues. And this is an analog of that. We have Walpole's theory, we have really important results like Wickham theorem, or we have Lyon's Papanicolaou-Vardan results. Those are amazing achievements. And then now we have to really get deep down and study the properties, and maybe devising certain very powerful tools to not just study those, but maybe if we are lucky, we can study other problems. Okay. Yeah, I think I'm done. Questions, concerns? Okay. Yeah, you guys are quiet, but it's understandable. I mean, it has been a long time online. Yeah, so great. Thank you all. I have to save my voice. I'm taking one more class and giving a seminar. So We have two more lectures to go, Monday and Wednesday. Again, on Friday of next week, I'm gonna release you guys. Please, again, spend the time to review everything. Send me questions if you have any. Just complete your two homework problems in problem set 2 and you're done. And then also spend maybe 5 minutes to do the evaluation form for me. I have no ideas about I haven't got actually any email about it, but I guess that is somewhere. Maybe it's sent to you or anything. I mean, in the pandemic, everything is sort of like scattered around, and we sometimes cannot keep track with everything. Or maybe I'm sort of maybe losing certain sort of sense of things. But anyway, oh, there's a chat or something. Oh, okay. Yeah, but it's weird. I didn't get any email, or maybe yeah, well, maybe I deleted it or something. Sorry if you get the emails every day. But I mean, I'm really hopeful that this is a class that we go through together, and I can actually give you a very systematic, and it's a beautiful book of parties. And actually, I'm quite happy that we have really covered essentially all of it. I mean, of course, surely there's certain little sections here and there I didn't cover, but with the two upcoming lectures with the last time behavior results, and we have really, I mean, done most of it, and I'm very happy. So thank you all again. It's probably a nice weekend. Stay safe and healthy, and enjoy the weather a little bit. I haven't checked the weather, but I think it's nice. Okay, so thank you, and and see you next week. Bye for now. Thank you.